Hi class. Today we're going to be looking at our last section of this chapter, which is linear programming. It's the day you've all been waiting for. Linear programming. Da, 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 da. All right, so example 1. We are going to actually, through this whole lesson here, we're going to work with one problem, and it's just, we're going to break it down into, let's see, 1, 2, 3, 4-ish, 5 kind of parts, but this is all one problem. So just to kind of give you an idea, linear programming is a big deal, but it is so applicable to real life. So it's really important that we learn how to do this, and it's not easy. So we're going to need to work on it a little bit. All right, so let's get started. Bottled water and medical supplies are to be shipped to survivors of an earthquake by plane. Each bottle or each container of bottled water will serve 10 people, and each medical kit will aid 6. If X represents the number of bottles of water to be shipped and Y represents the number of medical kits, write the objective function that models the number of people that can be helped. So we want to figure out the number of people that can be helped. Well, if X is the number of bottles of water and each container of bottles of water serves 10 people, so I guess X represents the number of containers of bottles of water. That should have been specified there. So we're going to get 10 times X, so 10 people for each container of bottled water. Plus, I can help 6 people for every medical kit that we ship. So this is going to be our objective function, and it's going to equal number of people we can help. All right, so objective function. So what's our objective? Our objective is to help people. So there's our objective function. Now, we also have some constraints. Unfortunately, we can't just send infinitely or infinite amounts of containers of bottled waters and medical kits. In real life, we have constraints. So let's look at what that is. Each plane can carry no more than 80,000 pounds. The bottle of water or bottled water weighs 20 pounds per container, and each medical kit weighs 10 pounds. Let X and Y represent the same variables. Write an inequality that models this constraint. So if each container of bottled water weighs 20 pounds, so 20 pounds for each container, plus 10 pounds for each medical kit, all of those pounds added together has to be no more than, so less than or equal to 80,000. So this is our plane weight constraint. All right, and then each plane can carry a total volume of supplies. So we can just kind of, let's just mark this plane weight. All right, and now we're going to look at the plane volume. So these are different. The X and Y still represents the number of containers and medical kits we're going to send, but we're looking at different parts or different categories, I can say, for each constraint. Okay, each plane, oops, that's supposed to say plane, not plan, can carry a total volume of supplies that does not exceed 6,000 cubic feet. Each water bottle is 1 cubic foot, and each medical kit also has a volume of 1 cubic foot. So they made it pretty simple for us. So 1 cubic foot for each container of bottled water, plus 1 cubic foot for each medical kit. All those cubic feet, when we take into consider how many medical kits and how many containers of water we're sending, cannot exceed, so again, less than or equal to 6,000 cubic feet. Okay, so right now, those are the only 2 constraints they've kind of laid out for us, but we're actually going to have 2 other constraints. They're going to be like hidden constraints, and I'll talk about those in a second. The situation above is an example of linear programming problem. Linear programming often asks us to maximize or minimize some quantities, such as maximizing profit or minimizing costs. We're going to use the corner points on our graph. So we're going to graph our constraints, and we're going to use the corner points as our possible solution, and then test each one with our objective function to figure out our answer. All right, so we want to determine how many bottles of water, so how many bottles of water, X, and how many medical kits, Y, should be sent on each plane to maximize the number of survivors who can be helped. So we want to get the maximum number of people we can help. So our system of constraints here, and actually I'm going to write it down here so I can see them next to my graph. I have 20x plus 10y less than or equal to 80,000. I have x plus y is less than or equal to 6,000. And then I talked about the hidden constraints. So there's two hidden constraints that we always need to think about. And that is so we've talked about they can't get any bigger than like 80,000 pounds or 6,000 cubic feet. But what about how small can the X and Y get? Well, I can't send negative bottles of water and I can't send negative medical kits. So I also need these two hidden constraints because we can't send negative things. We can send 0, but we can't send negative. And if we forget to write those constraints, our system is actually not complete. So it's really important that we think about those. Okay, so at this point, we're going to go to Desmos and we're going to graph the system. So I'm going to graph my first constraint, 20x plus 10y is less than or equal to 80,000. And if you notice, I can't see anything that's happening because 80,000 is really big. So you're going to want to go to your settings and you're going to want to fix this to be, and I usually just start by typing in zeros until I see something. Okay, cool. That looks good. And then same thing with oh, you know what? That's a little too big. I think I'm going to make this a little smaller. So go back to my y-axis. I'm going to try this again. Maybe 1, 0, 0, 0, 0. Yeah, just that many zeros. Okay, because I can move that up. And then my x-axis, I also need to change. And let's see, 1, 0, 0, 0 until I see that work out. All right, that looks good. Okay, so I can kind of see what's happening. And then you can zoom in and out and kind of move it around from there to get a better picture of what you have. All right, now if we turn on the other ones, there's my second constraint, and my hidden constraints are going to make it so they don't go down forever and ever. All right, and then, oops. There we go. So here is a picture of my constraints. And then what we want to do is just kind of click around. If we notice that one shades down and this one shades down. So I have this one, and then these ones both shade in the positive direction. So these 4 points are what we call our corner points of our feasible region. You're going to hear the term feasible region is that overlapping shaded region. All right, so we've got 0, 6,000. So I have to go all the way up to, well, let's see, where did this red one cross my y-axis? Just so I know how high I need to graph this thing, 8,000. All right, and then this line went all the way over to 6,000 over here. So I do need to make sure I've got those in my picture. Okay, so I need to go up to 8,000 on my y-axis and down to 6,000 or over to 6,000 on my x-axis. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. 9, 10, 11, 12, 13, 14, 15, 16. Ooh, that actually works well. So I'm going to make this 8,000. And then this is going to be 1, 2, 3. So I'm counting by 500s is what I'm doing. And then let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, I'm going to make this 6,000 and I'm counting by 500s. And then we need to, it's so important because this is a word problem. We have to label our axes. So X, this is my x-axis and my y-axis. And what did X represent? It was number of bottled water containers. And then Y represented the number of medical kits. So it's really important that we label that. Okay, so then I know that one of my lines went up to 8,000 and that red one crossed 4,000 down here. So 1, 2, 3, and 4,000. All right, so we draw that one. And then my other one was 6,000. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There's 6,000. Oops, did I do that right? Nope. Sorry about that. Get that other one out of there. Okay. And then 6,000 was here. So my other line does that. Okay. And then my feasible region is this shaded region in here. So, and then my intersection point, super important that we have all of our corner points. So one of my corner points was at 6,000. This was at 2,000, 4,000. All right. So this is 2,000, 4,000. I know my graph isn't perfect. Okay. So we have our 4 corner points. So now what we're going to do, now that we have a graph and it's fairly accurate, gives us a good picture of what's happening, we are going to list our corner points. All right, so corner points. My computer's lagging a little bit. We have the point 0, 0 and the point 4,000, 0. We have the point 0, 6,000. And we have the point 2,000 and 4,000. And now what we're going to do, so these are, again, numbers of bottles of water and numbers of medical kits. Now we're going to see how many people we can help. So we're going to look back at our objective function from the very beginning. So if you look back at example 1, we found out we can help 10 people for each bottle of water and 6 people for each medical kit. So number of people helped. So what we're going to do is we're going to show our work. We're going to plug our points, our corner points, into that objective function. So 10 times 0 plus 6 times 0. And I know that you might be thinking, well, if I don't send any medical kits or any bottles of water, I'm not helping anybody. And you're right, but we still want to show that work because it is one of the corners of our feasible region. All right, and then we have 10 times 4,000 water bottles plus 6 times no medical kits is going to give us 40,000 people. Let's see, 10 times 0. Oh my goodness, sorry. Plus 6 times 6,000 is going to give me 36,000 people. And then this one, I have a 10 times 2,000 plus 6 times 4,000. And if you plug that in, we get 44,000 people. So we have found the magic combination of numbers of bottles of water and medical kits that will fit on the airplane and help the maximum number of people. So then we want to write a statement to represent this. So oh my goodness, we can help. My pen is not working. All right, so here's the statement. We can help a max of 44,000 people by sending 2,000 water bottles and 4,000 medical kits. And that is a linear programming problem.